All right, everybody, welcome to our final class for Intro to Counting and Probability. Because this is our final class, I wanted our icebreaker for this week to be what would you like to see as our next Bridge to Math class? So let us know in the chat what kind of topics, programs, let us know what you'd like to see, and we will try our best to bring those kinds of classes to you guys. Yeah, I think we're gonna have a really great class today. Today we're gonna be doing a lot of problem solving, putting together everything you guys have learned. So yeah, it's gonna be fun. So yeah, kind of just going back to this, let us know what future classes you'd like to see. Okay, awesome. So I see a couple people saying programming. I see debate as well. That's cool. What language do you guys want to know for programming? Like Python, Java, C++? Maybe something else. Okay, so Hosher says Python. Awesome. Yeah, Python's pretty useful. And there's a lot going on with it, so it's good to learn for sure. Yeah. And I don't know if any of you guys are in our current programming class. Would you like for, if you are in that class, would you like for like a more advanced session with covering more advanced topics, or let us know? Okay, Manit says maybe a math counts course. Yeah, I know there's not much going on for math counts right now, but I think we will probably do a math counts course going into next semester, just because that's when your chapter in school run starts. Yeah, definitely we'll run another math counts course soon. Neha says the SAT prep. Yeah, that's a good one. I think we actually have a lot of elementary and middle schoolers, but if we do run an SAT prep course, we'll try to leave that for any rising high school students, just because that's when it's going to be most useful. Okay, cool. Ayush says a geometry class. Yeah, that's a good one. I don't think we've run a geometry course yet, but we're definitely looking to do that in the future. So we will definitely try to plan kind of around that. Yeah, thanks for that suggestion. Okay. Any other classes you guys would like to see, recommendations? We're going to be kind of making our course load for the upcoming month or so, upcoming like next couple of months. So we want to make sure we're getting you guys some new classes, and not some stuff that you've done before. So yeah, let us know. Oh, Manit says a debate class. Okay, awesome. Yeah, that's a good one. Cool. Okay, well, I will definitely keep these suggestions. And if you guys can think of anything else, feel free to shoot me an email, or text me, like just let me know. Send me some kind of information, letting us know what kind of classes you want. Also, just a little reminder, we will send out like an end of class form after this session, just so that we can get some feedback from you guys, and let us know what you think about the class. Okay, and with that, let's go ahead and jump into content. So like we've been doing for the past couple classes, I'll go ahead, lead off with some of the warm-ups, and then Sahasra will take over the second part of class and kind of go into the content for this week. Um, okay, awesome. I do see a question from Neha. Do we have any ongoing book clubs? No, we don't have a book club, but I like to read, so maybe we will start a book club. I think that's a very cool idea. Okay, anyways, on to the math. Let's go ahead and take a look at our first question. This is from a past contest, but it's a very, very old contest, so hopefully it's not super difficult. We want to find out how many whole numbers between 100 and 400 contain the digit 2. So I'll give you guys like maybe 30, 45 seconds to think about this, and then we'll go ahead and talk. Okay. I don't see any answers just yet, but that's cool. Let's just go ahead, get started, and maybe we'll see some answers trickle in. So to first start off, I think this is a problem where complementary counting makes a lot more sense because if you did some normal counting, you would have to do a lot of messy casework. And whenever possible, we always want to limit that casework. So let's go ahead and first find out our total number of cases. Remember, when we do complementary counting, what we want to do is take the total number of possibilities we have and then subtract the number of possibilities we don't want. So to start off, the total number of numbers from 400 to 100, pretty easy to count. We'll just do 400 minus 100 minus 1. The reason why we're subtracting 1 is because we're between this range. So that means we don't include 100 and 400. So when we go ahead and find this, we see that there are a total of 299 numbers between 100 and 400. Okay, so now we want to find out how many numbers don't have the digit 2. So if we go ahead and look at each place value, for the hundreds digit, we can have either a 1, we can't have a 2, but we can have a 3. So that gives us two possibilities for the hundreds digit. For the tens digit, normally we would have 10 possibilities, but remember that we can't have 2. That's not a possibility. So instead of 10 possibilities, we would have 9 possibilities for the ones digit or for the tens digit, and similarly 9 possibilities for the ones digit. So multiplying each of these possibilities together for each digit, we get 2 times 9 times 9, which gives us 162 ways that are not allowed. But in these 162, we also counted 100. That's when the first digit is 1 and these two selected are 0, which was included in here. But remember, that wasn't included in the range between 400 and 100. So we have to go ahead and subtract that case, meaning that there are a total of 161 total possibilities that we don't want to count. That means these are the numbers where there is no 2. Whoops. No digit 2. So because we want to find the number of numbers containing a digit 2, we will take our total number of cases, which is 299, and subtract the cases we don't want, which is 161. And that'll give us a total of 138 numbers with the digit 2. Awesome. I see Manit put in this answer, but I see a lot of people putting in 157 instead. So for those of you guys that put in 157, you definitely overcounted. So let me know if you guys see where you overcounted. If not, we can go ahead and run through the solution once more. Give you guys a couple seconds to look through your work again. But as you can see, kind of going with this complementary counting approach is much, much faster. And it's also easier, and you avoid double counting cases where maybe you have two twos, like 227 or something. Like that's something that can get a little tricky. So this kind of method accounts for that. Okay, yeah, sure. So let's go through this one more time. So basically what we're doing is we're taking a complementary counting approach for the reason that I just explained. So we first want to find the total number of numbers, which is 400 minus 100 minus 1, or 299. The reason why we subtract 1 is because we're not including the boundaries of 400 and 100. Then we want to find the number of numbers that don't contain a digit of 2. So we go digit by digit, and for the first digit, we can have either 1 or 3. We don't include 2. So that means there's only 2 possibilities. Then for the next digit, there's a total of 10 possible digits, but remember, we don't consider the 2. So that means there are actually only 9 possible digits. And for the same reason, there's 9 possible ones digits. So if we go ahead and multiply all of these possibilities together, we get 2 times 9 times 9, which is 162. But in this 162, we also counted the number 100, which I showed over here. So we need to subtract that because remember, 100 isn't contained in our total 299 cases. So that means there are 161 numbers where there's no digit 2. So to find how many numbers contain the digit 2, we'll take our total number of cases, which is 299, and subtract the 161 cases without the digit 2. And that gives us 138 numbers with the digit 2. So the big idea here is that we're taking a complementary counting approach to help us subtract what we don't want instead of going through casework to find what we do want, which is just the general rule of thumb for using complementary counting. Okay, awesome. Let's go ahead and take a look at our next question, which is similar because we're still dealing with digits. In case you guys haven't noticed by now, a lot of counting is working with numbers and digits. Okay, so in this case, we're working with a 7-digit whole number, and this is like a possible telephone number. So we want to find out how many telephone numbers don't begin with 0 or 1 and begin with 9 and end with 0. So this is kind of a probability question, um, if that helps you think on the right track. Okay. I do see some answers. I see 1 over 80 as a potential answer. I don't see anything else just yet. So oh, and I see 1 over 75 as well. Okay, awesome. Let's go ahead and take a look at this question. So we have 7 digits. One way some people might approach this is by counting how many total telephone numbers there are, and then also counting how many of those telephone numbers begin with 9 and end with 0. And that's totally a way to do this. It's just really long and really tedious. So instead, what we want to do is we want to find the probability of each event. So the first one that we want to do is finding the probability of a randomly selected telephone number beginning with 9. So that means we have to look at how many possibilities there are for the first digit. So the first digit, or actually, I should probably write this above the line. So this is our first digit. And we are told that the first digit can be any digit except 1 or 0. That means of the total 10 possible digits, there are 2 that it can't be. So that means there's only 8 possibilities for this first digit of the phone number. So of these 8 possibilities, we want to find out how many of them begin with 9. There's only one way for the telephone number to start with 9. So we have 1 out of 8 ways for the telephone number to begin with 9. That's that first probability. The second probability we want to look at is the probability that the last digit is 0. Now, there's no restriction on the last digit, which means that there's a total of 10 possibilities there, and only one of those is actually 0. So I'll have 1 over 10 possibilities for that last digit. And because the selection for the first digit has no relation to the selection for the last digit, we go ahead and multiply these probabilities together because they're independent events. So that means the probability that both events happen is 1 over 8 times 1 over 10, which is equal to 1 over 80. And that is our final answer, just like Aditya, Maneet, and Pranav all said. So really great job, you guys. Okay, awesome. Any questions about how that worked and also why we chose to go with this approach instead of counting? Okay, awesome. I see smiley faces, which is great. I always love to see smiley faces. So let's go ahead and move on to our next question. Great. This one is from a past contest called the American Regional Math League. And this is something that we kind of do in high school. I actually did this, I think last month, this competition last month. So it's very exciting. All right, so now we've got someone who's walking up some steps, and we want to find out how many ways he can walk up a 14-step stairwell. Okay. Let's go ahead and take a look at this question. And this is actually one where the best possible way to do this is casework. The reason why that is because there's not a lot of symmetry happening here. And also there's just so many different cases for us to consider. It's hard to group things together. So in this case, I would recommend taking a casework approach. So let's take a look. First, we see that he can take steps 1 or 2 times at a time. So to go up 14 steps, you can either take 14 one steps, you can take 12 one steps, and 1 2 step. You can also do 10 one steps and 2 2 steps, and this kind of keeps going until you get to, you take 0 one steps and 7 2 steps. So this gives us a total of 8 cases ranging from 0 2 steps to 7 2 steps. And each case has a corresponding 1 step. But in every single case, remember, there's no regular pattern for how he takes his steps. So that means the ways he takes his steps are also can also be arranged differently. So that means if we have a sequence of 14 one steps and 0 2 steps, we have to arrange these 14 one steps in 14 choose 14 ways. I mean, there's only one way to take 14 one steps. However, if we go to this next case, we'll see that we're taking 12 one steps and 1 2 step. So there's a total of 13 step objects for us to arrange, and 12 of those are the same. They're all 1 steps. So that means what we're trying to do is we're trying to choose 12 objects from 13 to see how to arrange those. So that is denoted by 13, choose 12. In a similar manner, we have 10 one steps and 2 2 steps. There's a total of 12 objects and 10 of them are the same. We need to choose how we're arranging it. So that comes out to be 12, choose 10. And then we kind of just keep going until we get to our final step, which is just 7 2 steps, which we arrange in 7 choose 7 ways. Okay, so now because these are all distinct cases, we have to add them up together. So I'm gonna go ahead and clear some space for this because this is actually quite a long calculation. Um, and this is probably like the worst case scenario for casework. But if you guys can do this, then you can probably do most casework questions. So bear with me here. All right, let's do this in a different color. So our different cases, the sums that we have to do is 14 choose 14. This is 14 one steps. Then you have 13 choose 12. This is 12 one steps and 1 2 step. Then you have 12 choose 10, which is 10 one steps and 2 2 steps. Then you have 11 choose 8, which is 8 one steps and then 3 2 steps. And then we kind of just keep going until we get to 10 choose 6, which should be 6 one steps and 4 2 steps. And then, or 6 2 steps, 4 one steps. There we go. And then we should get 9 choose 7. I think I messed up somewhere along the way. All right, let's double check. So we have 8 one steps and 3 2 steps, which is 11 choose 8. That looks good. And then we have 6 one steps and 4 2 steps, which is equal to 10 choose 6. That's also correct. And then we'll have our 4 one steps and 3 2 steps. Oh, not 3, 5 2 steps, which is equal to, oops, and that is going to be 9 choose 4. Okay, there we go. And then we will have 2 one steps and 6 2 steps. And that is 8 choose 2. And then we get to 7 choose 0 here, which is also the same as 7 choose 7. Okay, awesome. All right, let me know. Let's pause here. Let me know if this is confusing or if you guys want me to go over it again. I know we had a little blip there before. So if you need me to repeat that, let me know and we can go ahead and talk about it once more. Okay, more smiley faces, which is good. Yes, okay, awesome. And I see a lot of you guys have already went ahead and done the calculation and got 610, which is absolutely right. I'm not gonna do the calculation because this is honestly just a lot of arithmetic that you guys seem very capable of doing. If you want to see how it's done though, the arithmetic will be in the handout that is going to be sent out after class. But after this point, once you get the sum of all these combinations, you just got to do the math and grind it out to get 610. Okay, awesome. So let's recap really quickly how we even got this sum, because that's the most important part of this problem. What we're doing is we're looking at the different cases, and I think everyone understood the cases we were looking at. We're looking at how many cases or how many possibilities there are to pick 1-steps and 2-steps. So we start off with the most extreme case, which is 14 1-steps and 0 2-steps. And then we increment so that we're adding 1 2-step every time. So if we add 1 2-step, that means we have 2 less 1-steps. So I will have 12 1-steps and 1 2-step. And then I'll have 10 1-steps and 2 2-steps, and then 8 1-step and 3 2-steps, and then 6 1-steps and 4 2-steps, and so on, so that we get 8 total cases, which are all listed here. And then for each case, we want to find out how many ways there are to arrange the 1-step and 2-steps. So to do that, we take a look at how many groups of steps are being taken. So in this case, there's 14 groups being taken, and of those 14, they're all the same. So we just have 14, choose 14 ways to arrange them. For the next one, we have 13 total steps to arrange, and 12 of those are the same. They're all 1-steps. So we have 13, choose 12 total ways to arrange, and so on. We keep doing these combinations until we get this final sum. Okay, awesome. I see a hand raised from Minnie. Minnie, go ahead.
So I got 610, but what I'm not getting in the explanation is 10 choose 6 is already greater than 610.
10 choose 6. Let's take a look. 10 times 9 times 8 times 7 over, let's see, 720, right? Okay. You can cancel out a 10 over here, and that should give you 72. Should be only getting,
Oh,
yeah, I think so, right? Hold on, let's see. And then there's an extra 4 factorial, I think. Oh, I see what I did. Hold on. There we go. Let's redo that. So we'll have 10 factorial divided by 4 factorial times 6 factorial, okay? So that gives us 10 times 9 times 8 times 7 over 24. Sorry, that's the correct denominator. So when you simplify this, 9 times 8 is 72. 72 divided by 24 is going to be 3 in the numerator. So this is 10 times 3 times 7, which is equal to 210. So that is less than 610. Okay, awesome. My apologies for that miscalculation initially. All right, let's do a couple more problems and then I will turn it over to Sahasra. All righty. Okay. This one is a shift from all the numeric questions we've been doing with all the numbers and stuff. So let's take it a step back and do something a little easy where we're working with some words. So we want to find out how many unique 6-letter words can be formed using all of the letters in the word banana. All right, I see answers coming in quickly. This is good, you guys. I see a lot of people saying 60, which is cool. Thank you guys for putting in some answers. Awesome. And I think almost everyone knows how to do this. So let's go ahead and run through it really quick. So first we want to look at how many letters we have in total. We have 6 letters. And so there's 6 factorial ways to arrange that, except we're told we want unique words, and we have some repeat letters that we need to account for. So first of all, there are 3 A's, which can be arranged in 3 factorial ways. So that means of our 6 factorial, 3 factorial are duplicates. Similarly, there's 2 N's which can be arranged in 2 factorial ways, so those are also duplicates. So we have to account for those duplicates by division. And when we do that, we will get 720 divided by 6 times 2, which is equal to 720 over 12 or 60. And this could actually be a count-on question, given how simple the arithmetic is. So learn how to do these quickly. And if you guys have questions, please let me know, because this is a very fundamental concept. So we should clear that up as soon as possible. Okay, smiley faces all around. This is good. I think in my future classes, I'm just gonna ask people to start putting smiley faces in chat if they like are happy with what's going on, because I think this is great, you guys. This is awesome. Okay, and for our final question, which is probably one of my favorite questions in counting ever, it is also a very, very popular question type, but I like it nonetheless. We're going to find out how many ways one person can move from point A to point B. Give me a moment to get you guys that diagram, though. All right, here we go. Awesome. So this is our diagram, and we want Ira to go from this point all the way up to this point. All right. I see a couple answers coming in, but I'll give you guys more time. See 126 and 110. Awesome. Okay, let's go ahead and take a look at this question. So the way that we're going to do this is by looking at what every path has in common. You might think we have to do casework where we have to count like where the person can go in each direction or at each point. So for example, they can go either here or here, and then when they're here, they can go here and here, and then you kind of just keep doing that. But that seems very tedious and way too much casework and very easy to mess up. So instead, what we're going to do is look at what every path has to do. Because we can only go up and right, we can't go backwards to left, down, diagonal, none of that. We only go up and right. So that means every path from A to B has to go up 4 times, as shown here, and has to go to the right 5 times, as shown here. You can't go less than 4, you can't go less than 5. It has to be exactly 4 ups and 5 to the right, because otherwise you don't end up at point B. So let's go ahead and denote our ups as U. So this is an up step, and a right step is denoted by R. So one possible path would be U, U, R, 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 U, R, R, U. And that path looks like this graph. I'll show you guys here. The B got a little cut off, but I think you can get the idea. Let's move this over here and bring this up. Okay, awesome. So the path U, U, R, 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 U, R, R, U looks like 2 ups, 3 to the right, 1 up, 2 to the right, and 1 up. Isn't that weird? We can represent an entire path just by using letters. And the reason why that is because every path needs to have 4 U's and 5 rights. Otherwise, it's not a valid path. So now the question becomes, how can we arrange these 4 U's and 5 R's to get a distinct path? Well, that's a very easy counting question that you guys have done a ton already. So we're looking at 9 objects, and 4 of them are the same, and 5 of them are similar to each other as well. So that means of these 9 objects, we need to choose 4 ways to arrange those U's. So 9 choose 4 or 9 choose 5. Both are equal. So that means we have 9 times 8 times 7 times 6 divided by 4 factorial. Now we know 4 factorial is 24, and 9 times 8 is 72. So 72 divided by 24, that cancels out to give us 3. So we have 3 times 7 times 6, which is 21 times 6, or 126. And that is our final answer, which I saw in the chat. So excellent job, you guys. One kind of note about this question, this is a very good example, a very simple example too, of a one-to-one correspondence, which you'll learn a lot more about earlier. But this is a really important concept in counting that can simplify some really difficult problems. And the reason why that is because what a one-to-one correspondence does is it takes a complex problem and then finds a different way to represent it that is easier to count. So in this case, we were taking path counting and representing it using letters, and we're really good at arranging letters. So that's our one-to-one correspondence here. I do see one question. Why do we know that it's 9 choose 4? Remember, we are arranging 9 objects and 4 of them are the same. So by the definition of combination, there's 9 choose 4 ways to arrange 9 objects where 4 of them are the same. Okay, awesome. So that was all I have for the warm-ups. If you guys have any questions about this section, feel free to DM me, let me know. Otherwise, Sahasra, I will pass it over to you.
All right, hi guys, good evening. I'm just gonna go ahead and share my screen. All right, in today's class, we'll be focusing on two major concepts, conditional probability and expected value. And I'm gonna go ahead and explain what conditional probability is in just a second. So conditional probability is basically when you figure out the probability of an event happening given that an event already happened. So an example of this is this problem right here. When you know that an event has already happened, it narrows down the probability of a second event happening as well. So like there is in this definition here, conditional probability is basically the chance that an event occurs given that another event has already happened. So instead of listing all the outcomes, you narrow down the sample space for the second event. So let's go ahead and solve this problem here. Pretty simple. I'd like to see you guys answer it in the chat. Okay, I'm seeing a couple of people put 1/6. So, oh, and I'm also seeing 1/3. Okay, so first what you want to do is figure out how many even numbers there are because we know that we're working with only the even numbers because it says given that the number is even, what is the probability that it is a multiple of 3? So the even numbers on a 6-sided die are, give me just a second. Okay, so the even numbers on a 6-sided die are 2. Oh, that is very, okay. We have 2, 4, and 6. And we want to know out of these three numbers, what is the probability that it's a multiple of 3? So our only multiple of 3 here is 6. So that is one favorable outcome. And our total outcomes is 3 because remember, we're only working with the even numbers. So we have one favorable outcome and 3 total outcomes. So that means our answer will be 1/3. So there is a 1/3 probability that an even number on a die is a multiple of 3. All right, I hope that makes sense. A lot of you guys put 1/6, so I hope that makes sense why it's 1/3. All right, let's move on to our next problem. Okay, a class has 10 students, 4 play piano, and 3 of the pianists also play violin. If a student is randomly selected and they know how to play piano, what is the probability that they also know how to play violin? I'm seeing a couple of people putting 3/4 in the chat. All right, let's go ahead and solve this one. So we already know that 4 students play piano, and they also gave in the question that 3 of those pianists also play violin. So we kind of already have our favorable outcomes in the problem. So we know that 4 people play piano, and given that we're only working with the 4 that play piano, 3 of those 4 piano players also play violin. So we have 3 favorable outcomes basically. And these are our piano players and our violin players. And our total is going to be 4 because we're only working with those who are playing piano. So our probability that a piano player also plays violin is going to be 3/4. So yeah, I'm pretty sure all of you guys put 3/4 in the chat, and that's super cool. All right, let's move on to our next problem. This one is also on conditional probability. A fair coin is flipped and a 6-sided die is rolled, so 2 events happening here. What is the probability of getting heads on the coin given that the die shows a 4? All right, I'm seeing a lot of you guys putting 1/2, and that's absolutely right. This is kind of a trick question. The die doesn't really matter here because the coin being flipped and the die being rolled are 2 independent events, so their probabilities have nothing to do with each other. So as always, our probability of flipping a head on a fair coin is going to be 1/2, and so will it be here. So yeah, all of you guys put 1/2, and it's always really nice to see when you guys are all in agreement. Moving on to our next problem, and this one's not as simple as the previous one. I know it's kind of cut off on the end. What it says is a team of 3 is chosen from 4 girls and 2 boys. Given that the team includes at least 1 boy, what is the probability that it has exactly 1 boy? I'm going to wait for a few answers to roll in, and then we can get right into solving it. Okay, I'm seeing 3/5. Okay, I'm seeing another 3/5 as well. So let's get right into solving it. Hold on just a second. All right, so we know that there are 4 girls and 2 boys to choose from for the team of 3. And we already know, given that the team includes at least 1 boy, what is the probability that it has exactly 1 boy is what we're trying to find. So if the team includes at least 1 boy, then we can use complementary counting to figure out how many teams are possible from that. So we know that so here what we want to do is figure out the total number of teams possible, and from that figure out how many have at least 1 boy, and basically you do that by subtracting the number of teams that have no boys. So that's how complementary counting works. So our total number of teams possible is going to be 6 choose 3 because we have 6 people to choose from and 3 people we have to choose. So basically what we do here is 6 factorial over, hold on guys, I'm just making sure I didn't do anything wrong. Okay, yeah, so 6 factorial over 3 factorial times 3 factorial because it's n factorial over r factorial times n minus r factorial. And when we solve this, we get 6 times 5 times 4 over 3 factorial, which is just 6. So this cancels out and we get 20. So there are 20. Okay, so there are 20 possible ways that the team has. There are 20 ways that a team can be made. And from this, it's given that the team includes at least 1 boy. So, hold on. Manit has raised his hand. Okay. Manit, I'm going to let you unmute. Hold on just a sec. Okay, you should be able to unmute now.
How is it 20 ways? Isn't it 6 times 5 times 4? Which equals 120 ways?
Yeah, but like it cancels out with the 3 factorial. The 6 cancels out with the 3 factorial.
Oh.
Okay. If you guys felt like there was any other mistake, just please raise your hand and let me know. All right, so now we have our number of teams that include at least one boy. And now we want to figure out the probability that it has exactly one boy. In other words, it has two girls and one boy. So guys, give me just a second. Okay, so basically what we want to do here is remember if the teams with exactly one boy are teams with one boy and two girls, because there are 3 people in a team. So we can choose 2 girls out of. Okay, so we have 2 boys available out of, that's what's given in the problem. We have 2 boys available. So out of those 2 boys, we want to choose one of them. So basically what we do here is 2 choose 1, and we multiply that with 2 choose 4, because we have to choose 2 girls out of the 4 girls. So, oh, I just realized I'm not even sharing that part. Okay, so we do 2 choose 1 and 4 choose 2, because we have 4 girls available in the problem, and we have to choose 2 of those girls to be on the team. So when we multiply these 2 together, we get 2 choose 1 is just 2 factorial over 1 factorial times 1 factorial, which is just 2. And 4 choose 2 is, this is getting a little messy here. So, and 4 choose 2 is 4 factorial over 2 factorial times 2 factorial. And when we solve this, we get 4 times 3 over 2 factorial. And the reason I didn't write 4 times 3 times 2 times 1 is because it already cancels out with one of the 2 factorials in the denominator. So 4 times 3 over 2 factorial gives us 6. So there are, okay, I thought I saw a question. Okay, so yeah, we have, okay, so now we have to multiply these 2 together. Guys, I keep feeling like I'm making a mistake, so if you guys spot any mistakes, please let me know. I feel like I did something wrong. Hold on. Sam, do you spot any mistake that I made here? I'm just wondering if I made a mistake, because I feel like this is a different answer I'm getting. All right, let's proceed with this approach over here. So earlier we found out that there are, okay, I'm so sorry, guys. Okay, if I'm not wrong, then earlier we figured out that our teams with at least one boy is 16. So here we have, here since we want the team to have one boy and 2 girls, this is our probability that it has one boy and this is the 2 girls. So we multiply these together if we want it to have one boy and 2 girls. So 2 times 6 gives us 12, and our total teams with at least one boy was found to be 16, if I'm not wrong. So 12 over 16 gives us 3/4 as our final answer. And Mani is asking, but we already know that there is one boy. No, basically what we figured out there is the probability that the number of teams with at least one boy. That doesn't mean that there's exactly one boy. Does that make sense here? the question's asking what's the probability that it has exactly one boy. All right, let's move on to something a little different now. This is again within conditional probability. A bag has 5 red, 3 blue, and 2 green marbles. Manit saying for the previous, are you saying that for the previous question? 12 over 20? Oh. Okay, I'll take a look at that in just a second. In the meantime, you guys can solve this problem. I did see a lot of you guys put 3/4 for that one though, so. But I'll still check and verify if it's 12 over 20 or 12 over 16. Okay, for the previous problem, it looks like there was a slight mistake in the answer key that I had. So it said 3/4 was the answer, but Manit, you are absolutely right. It is 12 over 20, which simplifies to 3/5, not 3/4. Okay, now for this question, I'm seeing a lot of you guys put 5/8, so let's solve this one together. And I guess this is a fairly simple problem compared to the previous one. So here we have a bag that has 5 red, 3 blue, and 2 green marbles. One is picked at random. Given that it is not green, what is the probability that it is red? So we already have our given over here. We are already given that it is not green. So if it's not green, then it could be either red or blue. So we are left with these 5 red marbles and these 3 red marbles to choose. Sorry, 5 red marbles and 3 blue marbles to choose from. So here we want to figure out the probability that it's red. So out of these 8 marbles total, 5 red plus 3 blue. 5 plus 3 gives us 8. So out of the 8 total marbles, there are 5 red marbles. So that will be our favorable outcomes. We have 5 red marbles, and our total is 8. So our probability, given that the marble is not green, there is a 5/8 probability that it is red. So you all were absolutely correct. All right, let's move on to another major concept for today. And this is expected value. And expected value is a really nice concept, which I really like, which ties both counting and probability. So expected value is basically the average of all your outcomes so far. And you use that to predict the probability for the next outcome. So this will make a lot more sense when we're solving problems. But here I have put expected value is the long-term average or the average of the processes that's happened so far. And basically you multiply each outcome by its probability. Then you add all those probabilities to figure out what the probability of the next thing happening. So like I said, it'll make a lot more sense when we actually solve a problem. So let's just go ahead and do that. Okay, you roll a fair die and earn the number of dollars that's equal to the number you roll. And here we want to figure out our expected value. And I'm going to go ahead and solve this problem because I'm not seeing many answers. Okay, $3.5 per roll. Okay, so let's go ahead and solve this one together. So we know that the number of dollars that we earn is going to be equal to the number that we roll. So what we want to do is figure out our expected value, again, is our average of basically all the values that we have so far. So our possible values are 1, 2, 3, 4, 5, and 6 because it's a standard die. And the dollars that we earn is going to be equal to the number that we roll. So we figure out the average of all these 6 numbers. So we do that by figuring out the sum of the 6 numbers and dividing it by 6. So let's go ahead and do that really quick. So 1 plus 2 plus 3 plus 4 plus 5 plus 6 gives us 21. And that is what I saw someone put in the chat. 21 over 6 gives us 3.5. So we can expect to earn $3.5 per roll. All right, let's move on to our next problem. And we are kind of running out of time, so let's try to do this a little quickly. And you guys are putting answers in the chat really quickly, so thank you for that. You must be really good at it. So here's our next problem. A biased coin or an unfair coin has a 70% chance of landing on heads and a 30% chance of landing on tails. You win $2 for heads and lose $1 for tails. What is your expected value, or how much can you expect to earn from this? All right, so this one kind of has probability in it as well. So this one's a little different, so I'm gonna go ahead and solve it. Okay, I'm seeing 50 cents. Yeah, I'm seeing a lot of people putting 50 cents. So, oh, and 1.1. So let's see which one's correct. So we know that we win $2 when we land on heads and lose $1 when we land on tails. So basically what we want to do here is multiply how you're earning or your loss with that loss or earnings probability. So here we win $2 for tails, so that's 2 times our probability, which is 70%, which is 0.7. And we add that with our earning or loss for tails. So we have a loss here, so -1 because we lose $1, and that we have a 30% chance for that, so 0.3. So here we're doing 0.7 times 2 plus 0.3 times -1. Okay, and VT said she forgot about the bias part, no worries. So here we have 1.4 plus, well, technically it's a negative, so plus a -0.3. And when we solve this, we get 1.1. And that will be our final answer. That is how much we can expect to earn from this. All right. Yeah, and I did see Manit put that in earlier as well, so I'm glad you guys understood that. Okay, I'm glad you guys get it now. Here's our next problem. Pretty similar as well. A bag has 4 red and 6 green balls, or yeah, hold on. Okay, drawing a red one wins $3 and drawing a green one wins $1. Oh, Snehit says, can you go back to the last problem really quick? Of course. Do you want me to go over anything? Or so a quick recap of the last problem. Basically what we did is we multiplied our earnings or loss with the probability for that. So 0.7 times 2 for heads and 0.3 times -1 for tails. And 0.7 times 2 gives us 1.4, and we did the same thing for tails to get -0.3. And when we finally solve, we get 1.1 as our final answer. Okay, let's move back to this problem really quick. Okay. I don't think I see any answers for this one yet, so. Okay, let's go ahead and start solving this one. So even though they didn't directly give us the probability like they did in the coin question, we can easily figure it out. So here we know that drawing a red marble gives us $3 and drawing a green marble wins us $1. So the probability of drawing a red marble is going to be 4 because we have 4 red marbles, and our total, oh, okay, yeah, and our total is going to be 10. So 4/10 is our probability of drawing a red marble, and let's just go ahead and simplify that to 2/5. So like we did previously, we multiply the probability with its earning or loss. So here we know that drawing a red wins us $3, so we do 2/5 times 3. So let's keep that aside. And we know that drawing a green marble wins $1. So we know that the probability of drawing a red is 4/10, so that must mean drawing a green would be 6/10. So our probability of drawing a green marble is going to be 6/10. 6/10. Oh, let's bring this down here because not much space left. Okay, so we had 3 times 2/5 plus how much do we win when we roll a green marble? We earn $1 when we roll a green marble. So we do plus 1 times 6/10 because our probability of rolling a green marble is 6/10. And once we solve that, we get 6/5 plus 6/10. And that gives us 12/10 plus 6/10. Sorry, this math is getting all over the place. So 12/10 plus 6/10 finally gives us 18/10, which gives us 1.8 as our final answer. So we can expect to earn 1.8 or $1.80 if we randomly choose a marble from the bag. All right, I think we have time for one more problem. So okay, let's go ahead and do this last problem because we might not have time. Okay, I'm seeing answers really fast for this one. So you pick a prize numbered 1 through 5, with each number being equally likely. What is the expected number? And I think this is also pretty straightforward, just basic expected value. So here, all you have to do is figure out the average of the numbers from 1 through 5. So 1 plus 2 plus 3 plus 4 plus 5 over 5 because there's 5 numbers. And when you do the math, you can kind of go inward like this. So you get 6 plus 3, which is 15, over 5, which is 3, which is what I saw a lot of you guys type in super fast in the chat. So yeah, our expected number will be 3. And we actually do have time to do this last one right here. I hope we have enough time. So yeah. Two fair dice are rolled. You earn dollars equal to the product of those two numbers rolled. So how much can you expect to earn from this? Okay, since we're really short on time, I'm going to go ahead and try to speed run through this. So the products that we have possible are 1, 1, 1, 2, 1, 3, 1, 4, and so on. There are 36 possible products. So if we multiply 1 by all the other numbers, we have, I don't even know if I'll have time to do the math here because the calculations are pretty lengthy for this one. So basically you figure out all the possible products for the two dice. So like 1 times 1, 2 times 3, 4 times 5, those kind of things. So and you find the average of all those products to figure out how much you can expect to earn from these two fair dice. All right, and it is 8 o'clock, so we'll be wrapping up right here. Oh, and Money actually managed to calculate it. It's 6.666. Okay, you'll figure out what the right answer is in the handout because this problem is on the handout. It's the last problem. So yeah, I hope you guys enjoy the rest of your summer break, and I really enjoyed doing this class with you guys, and I hope you enjoyed it as much as I did. So bye. Hope to see you guys in future classes as well. And make sure to check out the handout as well as the homework and the solutions. So yeah, bye guys.